Hi, good evening. I'm Ilan. I'm from University of Malaysia, Pahang. So my topic would be review on thermal energy storage and eutectic nitrate salt melting point. Okay, now as an introduction, so due to increasing effect of massive climate change because of the greenhouse emission and the diminishing fossil fuels, okay, this has increased the interest in identifying an alternate and clean energy source. Okay, one of the most common alternate and clean energy source we look into is solar power. Okay, so the leading renewable energy technology is the concentrated solar power technology, CSP. So in CSP plant, okay, the sunlight is focused and converged onto a heat transfer fluid. Okay, using a broad array of mirrors. Okay, this heat transfer fluid is later stored as thermal energy storage before pumped into the power block. Power block where the energy is, okay, where the sunlight is converted into energy. Okay, now HCF, there are a few requirements where HCF need to be met. Okay, so it has to be less expensive. Okay, less expensive. Okay, the main cost in CSP plant is based on the heat transfer fluid. Okay, so if by reducing the cost of the heat transfer fluid, it will eventually reduce the cost, significantly reduce the cost in the CSP plant. Okay, the next one, you need to have a high boiling point. Okay, high boiling point is, by increasing the high boiling point, it will increase the efficiency of the CSP plant. Okay, when you increase the efficiency of CSP plant, okay, this is very ideal to increase the efficiency of CSP plant. Okay, the next one is high chemical stability. Okay, at higher temperature, it is difficult to maintain the chemical stability of the HCF. HCF means the heat transfer fluid. Okay, so what we need is, when you use a chemically stable HCF, okay, it will experience less corrosive. So which means you don't need to add anything to make it chemically stable at high temperature. Okay. Now next one is the good thermophysical properties. This is necessary to have efficient heat transfer during the heat transfer fluid flows in. Okay, these are the three blocks which we already discussed before. The first block is where the sunlight is converged onto a heat transfer fluid. The next block is the storage block where it is kept as a TES, thermal energy storage. The last one is the power block where the energy stored is later converted into a generated into a electricity. Okay, now thermal energy storage. Okay, so it's divided into sensible heat storage, latent heat storage, and thermochemical energy storage. Okay, first one, sensible heat storage. Okay, for sensible heat storage, we have a rock bed, we have a ceramic brick. Okay, so the beds can be used for solar application of medium, moderate, and high temperature. Okay, so the thermophysical properties of the stone, the energy contained in a pack in a bed storage system depends on many parameters. So it depends on many parameters like the rock size, shape, density, and heat transfer flow. Okay, now for ceramic brick construction and the structure. Okay, construction and structure cement with active or passive storage design may also be used. Then comes with the liquid. Okay, water. Water is the best storage at a low temperature. Best storage media for low temperature. Okay, it is widely used and it is widely used, available, and it is also cheap. Okay, this is used as a storage device and a transport means of electricity. Okay, due to high vapor pressure of the water, expensive insulation are required for the application at high temperature. So this means it is difficult to use the water at a high temperature, okay, application at high temperature. If you want to use it, you need an expensive insulation and containment resistant pressure. Okay, next one. Okay, another example of liquid based sensible heat storage is petroleum based. Okay, petroleum based oil. Okay, they have lower steam pressure than water that can work at temperature greater than 300 degrees Celsius. But due to stability and safety purposes, oil is limited to less than 350, and it's also costly, and it is highly corrosive and difficult to contain at high temperature. Okay, these are the example of the solid and liquid material. As you can see, rock, concrete, castable ceramics, water, engine oil. Okay, so if you can see, the temperature range are around 0 to 160, 260, 295. Okay, now thermochemical energy storage. In a chemical reaction, the chemical heat storage mechanism depends on energy released and consumed by reform and breakup of molecular bonds. So the heat stored is governed by the amount of storage content, the heat reaction, and the conversion scope. Okay, for thermal energy for thermochemical storage production, this is still undergoing a basic laboratory stage. Okay, and it is far from validated design and material to be commercially transferred. Okay, TCS is being examined in detail because when the chemical reaction partners are separately stored and because it may provide outstanding volumetric energy density. It is almost uncommon to store the energy. Okay, example of chemical heat storage material are given in the table, this table 2. Okay, you have ammonia, you have calcium hydroxide, calcium carbonate, metal hydroxide. Okay, next one is the latent heat storage. Okay, latent heat storage, it's divided into organic PCM, inorganic PCM, and eutetic. Okay, for organic PCMs, you have paraffin, fatty acid, alcohol. Okay, so this is a combination. Okay, for paraffin, it's a combination of CH3, CH2, CH3, Okay, okay. Now the melting point of the paraffin increases as the number of atoms. It increases proportionally with the number of atoms. Now, paraffin is cheaper, odorless, and non-corrosive to supercool. Okay, now this is chemically stable below 500 degrees Celsius with small change volumes after melting. The the downside of using paraffin is it has a low thermal conductivity and low density. Fatty acid have a low corrosiveness, bad smell, and high rates. Okay, now leakage during the melting process with regard to fatty acid. Fatty acids are actually environmentally friendly. Okay, now next one is alcohol. Alcohol, the cause and non-toxicity of the alcohols are minimal. Okay, it has the highest melting point and latent heat in organic PCM. Okay, these are suitable to use in medium temperatures. Polyethylene glycol, PEG. Change in temperature in PEG process is near to the ambient temperature, increasing with the molecular weight of the polymer. It dissolves in water while the hydrophobic ones in nature. Okay. Highest supercooling of all organic PCM. Compared to any other organic PCM, this has the highest supercooling, which is a disadvantage. The difference between the smelting and freezing point can reach as high as 30 to 40 degrees Celsius, which is not ideal. Okay. Table 3 shows example of non-paraffin materials. Next one is the inorganic PCM. Okay, these are metal alloys. Okay, it has high heat storage capacity, expensive. These are very expensive material. It melts above 300 degrees Celsius. Okay, high thermal conductivity, high resistance to corrosiveness. Okay, it has a minor change in volume due to the changes in phases and no subcooling. Okay, it experiences changes in their microstructure due to precipitation. Okay, salt hydrate. They have low specific heat, subcooling, insulation, and fusion heat reduction through incongruous melting. Okay, table 4 shows example of inorganic. Next one is eutetic. Eutetic is a mixture of organic, inorganic, or inorganic PCMs. These are overview of PCM. Okay, if you can see, sensible heat storage has a higher durability compared to latent and chemical heat. So commercially viable are, if you can see over here. Okay, now temperature, energy density storage. Okay, next one is molten salt. Okay, molten salt, especially nitrate salt, they are widely used and accepted. Okay, it does actually have a poor thermal conductivity, liquid leakage. Okay, which are major drawbacks of the molten salt. Okay. Now, in order to overcome these advantages, sometimes we will add in nanoparticles, or we'll actually use binary or ternary molten salt, which are more stable compared to a single salt. Okay, so now if you can see that, okay, there are few studies have been made on binary and ternary molten salt, which shows that, if you can look at the table number 6, okay, it shows that, okay, ternary molten salt have a lower melting point compared to binary molten salt. Okay, and if you can look at the table 7, shows that quaternary nitrogen salt has much more lower melting point compared to binary or ternary molten salt. Okay. This has been discussed by a few researchers. So why using lower melting point is important, because okay, when you use a lower melting point, it avoids the freezing of the HCF. Okay, when you use a low melting point HCF, okay, you will require a lower energy or lower heat to maintain the HCF in a liquid form. Okay, so when you require a lower energy or lower heat to maintain the HCF in a liquid form, means you can reduce the energy you use to heat the HCF. So by reducing the energy to heat the HCF, you are eventually reducing the cost of the CSP plant itself. So this is why reducing the salt, okay, reducing the HCF melting point is very important. Okay, by reducing the melting point, you will also increase certain thermophysical properties of the okay, in this case the nitrate salt. Okay, you can see that. Okay, now Bradshaw is known to reveal the mixture of anhydride composition belonging to the quaternary system. Okay, lithium nitrate, sodium nitrate, potassium nitrate, and calcium nitrate. These compositions have melting point lower than 95 and has a thermal stability up to 500, which means it has a very high thermal stability and low melting point. This is very ideal to be used in a CSP plant. So as a conclusion, it's evident from this review that choosing a good thermal energy storage material benefits CSP processors. Okay, an ideal TES material have good thermophysical properties such as high energy storage, good thermal stability, non-toxic, non-corrosive, non-flammable, high thermal conductivity, low melting point, compatible with the container, and etc. Okay, although it's difficult to identify a perfect TES, but many research have been conducted to improvise the current TES to match the requirement. Okay, water media storage is better as sensible heat storage compared to the solid media, as the temperature range and the heat storage are higher. Okay, molten salt are more suitable PCM, especially eutectic nitrate salts, compared to other latent heat storage, as it has high thermal stability, high energy storage, less corrosive, lower melting point. Okay, among the eutectic nitrate salt, quaternary nitrate salt has the lower melting point compared to single, binary, and ternary molten salt. The addition or increased weight percentage of lithium nitrate proven to be reducing the melting point of molten salt. For future studies, we can review on other thermophysical properties such as specific heat, thermal stability, and thermal conductivity of the eutectic nitrate salt. Okay, thank you. This is